The story of this film began about 20 years ago. We were transferring vascularized turkey tendons in our university research lab, and were struck by the intricacy of the vascular network. Thereafter, the Chinese School of Plastic Surgery discovered the notion of the retrograde flap, and we began to develop a technique for transferring vascularized retrograde tendon flexor transfers onto the cubital pedicle to get round the problem of reconstructing flexor tendons. Little by little, this new vision of anatomy began to throw light on the relationships between the tendons, the sliding sheaths, and the vessels, and to challenge the very foundations of the classical school of thought. During the revascularization following the release of a garret, we observed that not only the tendinous extremities bled with an apparently circular longitudinal and peripheral vascularization, in contradiction with the avascular theory that held sway at that time, but that there seemed to be a real continuity between the sheaths and the tendons, which was not interrupted despite the distension occurring during sliding. It was also clear from observing the behavior of the vessels of the common carpal sheath during flexion and extension that rather simplistic mechanistic explanations could no longer account for these phenomena, and that this apparent disorder and irregularity of shapes was in fact the basis of some other form of complexity that we still knew hardly anything about. In our attempts to find an explanation, we began detailed in vivo microscopic analysis of the distribution and mobility of the vessels using 25-fold video magnification. By looking at a vessel as a petrol pump, we were able to approach the problem more simply. There was this vertical structure looking like the main part of the pump, then the pipe, and finally the adjoining vessel, just like a car filling up at the gas station. The pipe seemed to move away as the car moved off and to fold up as it approached. Look at this sequence. A large vessel, vessel 3, is gradually moving behind vessel 2 and the pump during flexion, then goes past it while approaching vessel 1, which in fact is the car vessel, whose pump is slowly receding as the pipe extends to its maximum. Finally, vessel 3 has overtaken vessel 2 and has closed on vessel 1, which itself has receded from vessel 2. So several forms of speed and progression seem to exist in homogeneous living matter. Due to the influence of reductionist linear thinking, the only rational explanation used to be that vascular structures were reinforced by several coaxial layers of connective tissue, the closest to the tendon moving the fastest and the furthest away moving the slowest. However, that view of annular layers sliding together needed the existence of a hierarchical histological distribution to stand up to scrutiny. Yet in vivo observation made the notion unacceptable. This meant that we needed a new way of thinking, something posing the problem in terms of global dynamics, continuous matter, a theory involving the concept of a tissue continuum in total contradiction with the traditional view of sliding structures. Briefly, the notion of stratification and virtual space. In vivo observation, or with electron microscopy after dehydration, showed that this collagen network in fact formed continuous matter composed of billions of tiny disorganized vacuoles apparently arranged in a fractal manner. It was pseudo-polygonal, but with a very special dynamic forming of volume of glycolicin, whose surrounding was composed of type 1, 3, 4, or 6 collagen fibers of considerably different sizes, according to their anatomical location and the role they had to perform. In this chaotic, haphazard world, there was absolutely no geometric regularity, no linearity, just fractal chaos. This system is customarily known as the connective or areolar tissue, but we called it the multimicrovascular collagenic absorbing system. To our minds, it was a rubbery elastic system because its role is to avoid reaching a threshold of resistance at which the collagen might shear. It has to allow the tendon to move freely without transferring the movement to the surrounding structures. It also struck us that the biomechanical behavior of this shock-absorbing system could be accounted for by the theory of drawers. As the tendon moves, the first vacuole might undergo traction to a point where it triggers the adjoining vacuole into action. Then the third is triggered, and the fourth, to such an extent that the final vacuole remains almost inactive. Our second hypothesis was that the same process was involved, but that the pressure was distributed equally among the vacuoles. However, this meant we were still only in 2 dimensions and that our only explanation was based on linear processes. Yet we were sure of something. The tissue continuum, the existence of basic vacuolar-type structures and the presence of a shock-absorbing system, allowing the organs to act independently. This sliding tissue is to be found in every nook and cranny of our organism, in other tendons like the extensors, in the abdominal wall near the rectus abdominis muscle, in contact with the thorax near the latissimus dorsi muscle, in the retroconjunctival groove of the eye, and so on. Indeed, it would seem that this tissue serves to anchor the muscles and tendons and could even be their primary constituent material. Even structures not called upon to move as such, nerves and the periosteum, are composed of this tissue fiber, but with differences in their arrangement and size. The mesoscopic framework of living matter required a more holistic view to be fully understood. So we began to look at the cutaneous and subcutaneous structures, which we thought we would find to be more stable in this mobile tissular environment. By its structure and its role of enclosing the other sensory organs, the skin is more than just an organ. It's a set of organs which is anatomically, physiologically, culturally, and psychically complex. Of all the senses, touch is the most fundamental. You can survive without smelling, seeing, or tasting, but not without touching. The skin permanently relays information. It never shuts down, blocks up, or sleeps. It has an odor, a texture, it perspires, secretes, eliminates. It exchanges signals with the outside world. Thanks to the skin, the body's surface is as much a machine for communication as a protective barrier. It can change color, texture, and shape, and retains the vestiges of aggression, such as sunburn, scars, and disease. At birth, it is taught, ready for life. Then, little by little, it ages, gets wrinkled, folded, and sags. Whether in newborn babies, adolescents, or adults, the skin is never totally flat and smooth. Through the hairs on its surface, you can see pseudogeometric structures separated by strength lines, allowing movement in all dimensions of space. These triangular pyramidal structures move in relation with each other. With any movement, they immediately align themselves with the traction. Their former position disappears, and a new shape is adopted. Then, as if by memory, they return to their initial position. With every single daily gesture, be it a caress or a fall, the skin undergoes this form of translation, traction, and stretching. Yet, with the exception of open wounds, it returns to its initial position. Of course, this movement has been known since time immemorial. It's called elasticity. But the question is, how is this elasticity linked to the subcutaneous structures? With the aid of a video endoscope, we began to stroll around under the skin to try to understand this apparently simple word of sliding, mobility, and smooth, slippery surfaces. We wanted to find out how it could accomplish both fast, sometimes violent movements, and gentle, minute ones without the slightest jerkiness. Dissect with a surgical blade, and what do you see? Just a wealth of tissue connections, a histological continuum, without any clear separations between the skin, the dermis, the hypodermis, the vessels, the aponeurosis, and the muscles. How is it then that this can all move so smoothly, and how can sliding come about? When you look closer, you can see that just below the dermis and hypodermis, there's a highly mobile tissue encompassing everything else and penetrating what is known as the undermined plane. When this tissue is tracted upward, you get a surprise. Curious movements occur due to the bursting of vacuoles at atmospheric pressure, demonstrating the existence of hydraulic systems under different levels of pressure. The show is total with pseudogeometrically shaped fibrillar structures encompassing the muscles, skin, and fat. Yet what are these shapes? What do they do and why are they there? Is this what we have traditionally termed the connective tissue? Let's now delve into this world of fibrils. How are these structures organized? How do they resorb and move, and what role do they play? To use the jargon of physical mechanics, the arrangement can be termed a complex one, completely stable and in search of equilibrium. A system with tremendous capacity to resist and adapt to change. For physicists and doctors alike, there is no other such entity with so much cacophonous movement on the microscopic and macroscopic level. Movements involving the muscles, fluids, fibrils, and cells. Here we are at the very heart of complexity. A Capernaum of collagen bathed in glycolicin with reservoirs of fatty microglobules storing energy, information, and matter. A communications network for exchanging energy, matter, and information between the component parts of the system and the various reservoirs by way of a torrent of blood rushing between the nerves, veins, arteries, and cells. Within this global network encompassed by the skin, you also have valves able to increase or decrease the flow of information in terms of intensity and speed. This multi-microvascular system, which at first sight seemed chaotic and complex, is therefore a set of elements with a large number of non-linear interconnections and arranged with a universal aim in mind. To promote life, to subdivide, to multiply according to preordained criteria such as the level of oxygen, the temperature of the body, and the composition of the plasma. This internal state of equilibrium must be maintained at all cost.